Alrighty, folks, so section or unit 8.3, the unit circle and trig ratios. This will be part A of the notes or part 1, whatever I call it on YouTube. I'm not sure right now. We're going to start by talking about the unit circle. It's literally a circle with radius of 1, unit circle, and it is centered at the origin at 0, 0. Since this is the unit circle, whenever it hits one of our axes, which we'll call quadrantals, the quadrantal angles, whenever it hits one of our axes, we know what the coordinates are at that intersection. Like right here, since it's on the x-axis, is 1, 0. Up here, 0, 1. Back here, -1, 0, and down here, 0, -1. And the last, what was it, 2 lessons ago, I think? What did we do yesterday? What did we do yesterday? Area and arc length. Oh, so we did radians the day before? Okay. So we have talked about radians and degrees, right? From here to here would be 90 degrees, right? Okay, I don't want to talk about 90 degrees. I want to talk about how many radians that is. Since a full circle is 2 pi radians, we could say beginning at the positive x-axis, because all angles begin at the positive x-axis and then open counterclockwise. This is 0 radians, but it's also 2 pi radians because it's all the way around the full circle. That means halfway across the circle would be where we find pi radians. Halfway between 0 and pi then is 1/2 pi, or pi over 2 radians. And halfway between 1 and 2 is 1.5, 3 pi over 2. Good with those ideas? Good, because it will be very important that you understand when I say, well, what are the coordinates at pi over 2? I'm really asking you to tell me 0, 1. So I say at pi over 2, I mean the angle pi over 2 radians. All right? Yes? Okay. Well, this is a circle. Do you guys remember how to find the equation of a circle from geometry that's centered at the origin? X squared plus y squared equals r squared. Remember that from geometry? Oh, COVID time, so you cheated. Got you. X squared plus y squared equals r squared is the generic equation of any circle centered at the origin. However, for our circle, we know what r is. It's 1. So for the unit circle, the equation is x squared plus y squared equals 1. Oh, wait. Goes here. There we go. Because that is the answer to that part. Okay, now I've already kind of let this cat out of the bag, but when you're measuring your angles, you measure your angles beginning at the positive x-axis. That would be 0 degrees, and it's also 0 radians, and they're going to be measured counterclockwise. So it says suppose P is on the unit circle and the point A is at 1, 0. So what we're saying is we could call this point right here A. Now point P is just somewhere on this unit circle. It doesn't say where it is. We just know it's there somewhere. So I'm going to throw it on here, and I just for funsies, I put it over here because why not? The angle that would be created has its initial side as the positive x-axis right there, and what we call the terminal side right there. Terminal meaning where we stopped going around this circle. It says let theta be the angle that is measured from OA and it finishes at OP. I'm sorry? The O stands for origin. Yeah, so it's always in the middle. Great. Theta is a positive angle, so it would be done like this. That's what that would look like. And that's just me showing you the motion of this line segment OP. Imagine it was OA. It was laying on top of OA, and then it opened as if the origin was a hinge. And I'm showing you that it's opening counterclockwise. You see, as angles open counterclockwise, they'll be positive. But if they open the wrong way, which means clockwise, they'll be negative. Our angles are always read from the positive x-axis. That's always where angles begin. Positive x-axis. So angle O is positive, angle theta is positive because it's going counterclockwise. However, that is not the only angle that would get us from here to here, because I could have also just done this. Now that wouldn't be theta, that would be some other angle. Another Greek letter that is commonly used for angles is phi, P-H-I, phi. So we have theta and phi. So we have theta is positive because it's counterclockwise, and we have that phi is negative, it's a negative angle because it opens clockwise. But notice that angle theta and angle phi land in the exact same spot. So you know what we call those two angles? We call them coterminal, meaning they terminate in the same spot. These are coterminal angles. And this is an important concept in trigonometry, coterminal angles, because honestly, if I was just trying to get positive answers only, I do have a theta that goes from here to here, but I could get another positive angle that's coterminal that lands in the exact same spot simply by turning a full circle. Because if I allowed theta to keep going one more full circle, it would still land in the exact same spot. So turning 360 degrees, which means going 2 pi, is essentially the same as going nowhere. Because adding 2 pi is like adding 0, because 0 and 2 pi radians are in the exact same spot. So this angle is theta. It's also theta plus 2 pi, 4 pi, 6 pi, 8 pi, so on and so forth. Cool with that? And it's not super important, but I do want to mention it. What relationship do theta and phi have other than being coterminal? They add up to 360. Yep. That's not really all that important, but hopefully you see it, because that'll come in handy when you're doing arc length style questions and sector area style questions on your upcoming test. So we can say that phi equals 2 pi minus theta if you wanted to. Okay. So what I have here is quadrant 1 of the unit circle. And since it is the unit circle, we know that this radius is 1. Here's what we don't know. We don't know what the coordinates of P are. We do know that they're in quadrant 1, so it's a positive x and a positive y. Can we agree to that? Can we also agree then that from here to here is the x value of point P? We can all agree to that? And can we agree from here to here is the y value of point P? Yeah, good there too? Awesome. I'm sure you've heard of this before. SOHCAHTOA. SOHCAHTOA is the acronym that helps us remember which side lengths are associated with the 3 common trig ratios, sine, cosine, and tangent. Please don't say sin, cos, and tan. I will correct you. It's sine, cosine, and tangent. It is a sin to say sin. It's sine. That was a joke. But anyway, so The O and the H stands for opposite and hypotenuse. So sine of theta is the opposite side over the hypotenuse. It's important for me to mention that theta is always measured from the positive x-axis to the terminal side of the angle, okay? Theta will never be up here. Theta will always be centered at the origin. I want you always remembering that. Don't ever put it up there. That's a big fat no-no. It's always down here at the origin. Regardless of where, I mean, if I draw it down here, it's still at the measuring close to the origin, never out by the circle itself. Sine of theta uses the opposite side over the hypotenuse side. But in this triangle, from theta, what is my opposite side? You can say it louder. Yeah, y is the opposite side. And what is the hypotenuse? 1. So in the unit circle, sine of theta is y over 1, which is just y. Oh, okay, sine of theta is y in the unit circle. Cool. Cosine. Let me grab the green pen. I'm feeling green. CAH. So cosine uses the adjacent side over the hypotenuse. So in our unit circle, we come back over to this picture and I ask you, what is the adjacent side to angle theta? It is x, and the hypotenuse is still 1. Which means in the unit circle, cosine of theta is x. Huh, interesting. And tangent, TOA. Tangent uses the opposite side over the adjacent side. You guys have already told me that the opposite side is y. You've already told me that the adjacent side is x. So tangent theta is y over x. What does that imply? Do you see it? Anybody see the implication of saying tangent theta is y over x? That means that tangent of theta is sine theta over cosine theta. That's called a trig identity. Pretty neat, isn't it? So what we have here is very, very important. I need you to let go of opposite, adjacent, and hypotenuse as fast as possible. Just like I told you, I need you to let go of degrees as fast as possible. Instead of opposite, adjacent, hypotenuse, I need you to be used to using x, y, and r. X, y, and r are our friends. I don't know the unit circle. Shocking to anybody that had Miss Klein last year. But I can evaluate any trigonometry that I want to because I know how to build the unit circle. I never bothered memorizing it. I don't believe in memorizing things without understanding where they come from. Even then, I try not to memorize things. I mean, I barely know half your names. So, you know what's funny is that's actually true in some of my bigger classes. What? Yes, Bob, I know your name. I'm on video right now. Don't try to make me look bad. Serena? What's her name? I'm just kidding. Anyway, you threw me off track. What was I doing? Oh, okay. So X, Y, and R, super, super important. Cool? Trust me on this. You need to know those things. Now, trigonometry, sine, cosine, and tangent, it's a function. That means it has input and output, right? The input for trig is always an angle. The output for trig is always side lengths. So what does that tell us? That tells us that trig gives back sides. Trig takes an angle and gives us back sides. But here's the thing. Anything in math that can be done can be undone. So these functions, sine, cosine, and tangent, have inverses called sine inverse, cosine inverse, and tangent inverse. So sine inverse, I'll do it in blue so they match, looks like this. Don't say sine to the -1, please. No, that's sine inverse. It's the function that cancels the sine function, meaning it could be done on both sides of an equation. So if I took sine inverse here of both sides, it will give me sine inverse of the side lengths. And what will be left over here after sine and sine inverse cancel each other is theta. Same thing would be true for cosine inverse. And tangent inverse. The inverse symbol does not mean raised to the -1 power. But I would like you to look at the outputs of all three trig inverse. Trig takes thetas, gives us back sides. Trig inverse takes sides and gives you back angles. So the result of all trig inverse is an angle. Really important concept to know that trig returns sides, trig inverse returns angles. In my notes off to my side over here, I wrote that opposite is over here and adjacent is over here. But you guys pretty much knew that. Opposite means across from, adjacent means next to. Okay. And I wrote a couple more things. First of all, up above, I want to think like an IB student now. We reviewed that in the unit circle, x squared plus y squared equals 1. And then down here, we came across the result that sine of theta is y and cosine of theta is x. Therefore, yep, what we get is, and if you're okay with it, since the order of addition doesn't matter, I'm going to say sine first, but that's only because I'm used to saying sine first, because SOHCAHTOA. That means sine theta squared, which looks like this, sine squared theta, plus cosine theta squared, which looks like this, equals 1. And you know what's neat about that? It's true in any circle, regardless of what the radius is. Sine squared plus cosine squared always equals 1. Now, I know I'm being lazy and not saying theta. I hope you don't mind. But sine squared theta plus cosine squared theta will always equal 1, as long as it's the same theta. That is called the Pythagorean identity, because it looks like the Pythagorean theorem, a squared plus b squared equals c squared. It is arguably the most important trig identity there is. And it's one of the few that I have memorized. I try to memorize as little as possible. This one was very easy to memorize because I know exactly where it comes from. It comes from the equation of a circle with radius of 1. One more thing I want to put on this picture. Right there. Since point P is xy, and since I'm in the unit circle, point P's coordinates could have been written as cosine theta comma sine theta. And in all actuality, every single point in the xy coordinate system, known as the Cartesian coordinate plane, can be written in terms of trigonometry. They don't all have a radius of 1, obviously. So if you have something, a radius other than 1, then that radius would be right here. I mean, I told you sine was opposite over hypotenuse, which is y over r, right? Well, you could isolate this y, regardless of what this number was, by multiplying it to right there. So if I told you sine of theta was y over 5, then y would be 5 sine theta. That means every single point in the Cartesian coordinate plane, and this is for any circle, can be written as r cosine theta, r sine theta, regardless of what the radius is. Any x comma y can be written in forms of trigonometry, which is really, really incredible, at least for me, because I'm a huge nerd. It says use a unit circle, which I'm not going to do, to find the values of these two things. First of all, degrees. Ugh. Okay, but we got to do what we got to do. Okay, now degrees are awful. Give them up. No, you don't. Quick. How many degrees are in 5 full circles? You already failed. The answer is 10 pi radians. See how fast it is in radians? Yeah. I don't know what 360 times 5 is right off the top of my head, but I do know what 2 times 5 is right off the top. I know, but my point is it's difficult with degrees because of how large those numbers are. You know? And I mean, if I said, quick, 310 degrees, what quadrant is that? You're now trying to see it in your head. You're trying to figure out where that is, right? Pain in the butt. But if I gave you that number in radians, as long as you know that it's bigger than 1.5 but smaller than 2, you're in quadrant 4. You see? And so radians are just our friends because they're much smaller numbers. Also, radians are a universal truth, whereas degrees are completely made up. I mean, they are 100% made up. Okay, so yes, I will use degrees. Sine and cosine of negative 270 degrees. Yuck, yuck, yuck. So what does negative 270 degrees mean? It means start at 0 degrees and go negative. That means open clockwise. From here to here, how far was that? 90 degrees, so that is a negative 90 degree angle. And then if I go to here, how far have I gone? Negative 180. And then to here, it's 18 plus 9, folks. Negative 270 degrees. You know what is coterminal to negative 270 degrees? Positive 90 degrees. So these could have said cosine of negative degrees and sine of negative degrees, or even better, sine and cosine of pi over 2. That's even better. But they didn't. Regardless, we're going to say in our unit circle, what is the coordinate of this point? What is the x comma y of that point? 0 comma 1. Great, because cosine of theta is x over r, and sine of theta is y over r. Both of them have an r of 1. So cosine is just x. And sine is just y. How about that? Or you could have remembered that every point in the Cartesian coordinate system is cosine theta comma sine theta. So 0 is cosine theta, 1 is sine theta. That's just another way of seeing instantly what it is. So let me ask you a question. If you were here, how would you have done opposite over hypotenuse when there's no stinking triangle? Exactly. You have to use the coordinates. You have to use x, y, and r to figure out what that is. You're not going to be able to use opposite and adjacent here. I mean, you could know that this is hypotenuse, but you can't use the words opposite and adjacent when you're vertical or horizontal. It doesn't make any sense. But x, y, and radius always make sense. Okay. Periodicity. What that means is things that repeat. Periodic things repeat. And since there are 2 pi radians in a full circle, I've already mentioned this, but adding any integer multiple of 2 pi to theta is the same as not moving because you just went a full circle. It's the same angle. It would be coterminal every time you add or subtract 2 pi. That means for sine and cosine, and we are saying thetas and radians, as long as k is an integer, and we're using k to stand for constant, but we don't want to use c because cosines, we're using k for constant. As long as k is an integer, we get this result. Cosine of theta plus 2 pi times any integer, positive or negative, is exactly the same thing as not moving. And we get the same result for sine. Any integer multiple, positive or negative, of 2 pi is the same as doing absolutely nothing. What do we think about that? It's an okay concept? Understand what's happening there? It won't make it to the video, but if I were to, see, I'm looking at you right now, and if I were to spin 360 degrees and your eyes were closed when it happened, when you opened them, you wouldn't have known that I did anything, right? As long as you didn't hear me go, whee, as I was spinning, you wouldn't know anything happened. But that's because turning a full circle is the same thing as doing nothing. And it actually doesn't matter the way in which you go, clockwise or counterclockwise, that's why positive or negative k. Cool? However, what happens if you don't go the full circle? What happens if you only go half a circle? Like what you see here. So here we have a point, cosine theta comma sine theta, and we go half of a full circle, which is the same as going pi, because 2 pi is a full circle. So you go half a circle, you've gone pi. Also remember pi radians is 180 degrees, half a circle. What happens? Well, here I'm in quadrant 1. And in quadrant 1, my x comma y are both positive. You go half a circle, and look where you land. In quadrant 3, what do we know about x and y in quadrant 3? They're both negative. That means this coordinate, if you go 180 degrees, if you go pi radians, gives you negative cosine theta, comma negative sine theta. But Mr. M, that only worked because you were in quadrant 1 and 3. Actually, that's not true. It's actually not true. Another reason why, I just want to say it, another reason why this would be negative cosine theta and negative sine theta is because since cosine is x over r and radius can never be negative, down here you have negative x's and you also have negative y's. That's why sine is negative as well. X, y, and r, everything's about x, y, and r. So what did this tell us? This told us that if I took this theta and I added pi to it, this would be my result. If I took this theta and added pi to it, this would be my result. So what we know is that cosine of theta plus pi will give us negative cosine theta. And sine of theta plus pi will give us negative sine theta. And you will notice when written like that, no circle, no quadrants are necessary. It actually doesn't matter what theta is and where theta is. If you add pi to it, you have changed the symbol in front of cosine and in front of sine. What does that tell you about tangent? Well, we said earlier that tangent of theta is sine theta over cosine theta, right? We said that, right? So what is tangent of theta down here? Well, it's negative sine theta over negative cosine theta. And last time I checked, dividing two negatives just cancels out. Isn't that interesting? going half a circle did absolutely nothing to tangent, because here tangent was sine theta over cosine theta, and here pi radians later tangent was negative sine theta over negative cosine theta, which is still sine theta over cosine theta. For sine and cosine, going the full circle was the same as doing nothing. But for tangent, going half a circle was the same as doing nothing. And that's really important stuff for graphing purposes as well. Sine and cosine both repeat themselves every 2 pi. Tangent repeats itself every pi. And that's all the information. We haven't done any actual practicing yet, but I feel like that's a great place to stop for today, and we will do the practice tomorrow. Awesome.